So at this point, we've been dealing with normal force for a while, a few weeks. And so far, every single situation that we've dealt with it in, it has been a flat surface. Okay, we've had some different cases where we've got additional forces downward, additional forces upward, forces at angles, and all of that kind of either adds or subtracts from your normal force. That normal force is a reactive force canceling out your weight pulling downward. All right, but you're not always going to be standing on a horizontal surface. You may have vertical surfaces that are applying a normal force backwards, but more often, you might also have something in slant. Okay, so when we start talking about things on ramps, like if this block was sliding down this ramp, much like we'll do in a lab later, how are we going to figure out our normal force? Okay, because if we draw the forces on this thing, you've still got weight pointing downward, right? That'll point straight down towards the center of the earth. Okay, so you've got FW going down that way. And then the only other force acting on this block, and we are starting initially with a frictionless ramp. Next set of notes we'll cover if we add friction to it. But the only two forces we've got acting on this thing are the weight pulling downward and the normal force, and this is in the definition of what normal means in physics. Normal in physics means perpendicular to. Okay, so if our surface is here, our normal force will be at 90 degrees to it, pointing up from that surface. So we will have a normal force going off this way. So, let's think about what this block is doing. All right? If you don't have friction to slow the block down, clearly it will begin sliding downhill. But it's not moving into the ramp. It is sliding in a direction parallel to that ramp. Okay? So from that, we can use Newton's first law to try and figure out what that normal force has to be. Okay? Because if it isn't accelerating into the ramp, that means that any forces pointing directly away from the ramp and any forces pointing into the ramp need to be equal and opposite. They need to cancel out so that our net force in the direction that is perpendicular to the ramp cancels out. The only force that should be left over should be a force pulling it in the direction of the ramp, a force pulling parallel. Okay? So to do this, we're going to do a little bit of triangle trickery with our weight. All right? Because it's actually the direction of the weight that makes this difficult. It's moving parallel to the ramp. Our normal force is perpendicular to the ramp. We've got right angles there. It's this weight that's actually messing things up. Okay? So, the way that we can fix that is the same way that we fix any vector that's off at a weird angle and we want to add it to other things. We're going to split it into components. The components we're going to split it into here are going to be parallel to the ramp and perpendicular to the ramp. These are components of our weight. Right? If we look at our weight, it's pulling straight down. But as a result of that, the block is being pulled onto the ramp and it's being pulled down the ramp. We can split it into two separate vectors that when added together give us our weight. Okay? So just like we would with any other component vector, we're going to have one side and another side. Now I'm drawing these as dotted lines because they are not actual forces acting on the block. These are not separate forces. There isn't a separate force pulling it onto the ramp. There isn't a separate force pulling it in the direction of the ramp. These two forces, mathematically added together, would give us our weight. They are not actual forces though. All right? Basically, we are simplifying our weight, which is often an angle that makes it difficult to work with, into these two forces, which are at right angles or parallel to our ramp itself. Okay? So labeling these, this one is a force that is parallel to our ramp. So we're going to use an F, and we're going to put a little subscript, two vertical lines, two parallel lines. F parallel, the parallel component of our force. All right? This force is perpendicular to our ramp. Okay? So we're going to put an F for force, and then a little subscript set of perpendicular lines. Okay? So we have split our weight into two separate components. All right? Now, one thing I do want to point out. If we complete this triangle, right, because we've got this perpendicular side here, and we've got this parallel side, which would actually be equivalent to the parallel side over here, what it ends up making is a triangle. Okay? Not only that, if we were to flip that triangle, you would notice that the angle of the ramp is the same as the angle in there. Okay? These are similar triangles. Basically, we tilted the world some angle theta, and the angle being formed between weight and its two component vectors is the same angle. It's just a similar triangle. Okay? So, anytime that you have to use an angle, looking at those component vectors and your weight, that angle will be the same as the angle that your ramp has been raised up to. Okay? So, let's see. Let's label our little triangle here. We've got weight on one side. We've got our parallel force on the other side. We've got our perpendicular force on the other one. And we know theta. Okay? Let's say that we wanted to find one of these forces. Right? Let's say that we were looking for our perpendicular force, the perpendicular component of our weight. Okay? One thing you'll usually have is the weight of the object. In most cases, it will tell you you have a mass of usually 5 kilograms, because I'm lazy and I like 5. It's a nice number. So you'll be able to figure out your weight going downward by just doing mass times gravity. Okay? Now, if we're looking for that perpendicular side, you'll also probably be able to measure the angle of a ramp. It might tell you the length of the ramp or the height that it has been raised to. One of the main causes of difficulty in this is identifying what sides it's telling you. If it ever tells you the length of the ramp, that's telling you the hypotenuse. All right, I've had a lot of people in previous years use that as the adjacent side. All right, the ramp, what it's sliding down is the hypotenuse of that triangle. Okay, so now if we're looking for that perpendicular side, the component that is pointing directly into the ramp. Okay, well, we've got our hypotenuse, we've got our angle, and we're looking for that adjacent side. So the trig function that involves those, adjacent, hypotenuse, and angle, that would be cosine. Okay, so moving stuff around a little bit, cosine of our angle is equal to our adjacent side, our perpendicular force, divided by our hypotenuse, our weight. Okay, but we don't want to solve for cosine theta, we want to solve for perpendicular. So that would mean we would multiply over our FW. Right, there's going to be a very similar relationship with all the other ones that involve trig functions. You're going to have your weight times some trig function theta. Okay? Now, in case you don't feel like finding what that weight is first, or it just doesn't ask you, all right, we could also rewrite weight. All right, we could definitely do that. All right, so weight is just equal to mass times gravity. So another way to write this formula is mass times gravity times the cosine of your angle. Okay, these are the same formula, except instead of FW, we're putting in mg. It's equivalent to weight. It's mass times gravity. All right, but just in case you weren't asked for weight, you can just go straight to mg cosine theta. Okay, so next part, looking at our parallel component. Okay, now if we look at our little triangle that we completed over here, that is the opposite side. All right, now if you've already found your perpendicular component and your weight, you could find that opposite side using Pythagorean theorem, but right? This is a triangle. Let's use a trig function. Okay, so your general formula for finding your parallel side, all right, that opposite side, you've got opposite, hypotenuse, angle. That's going to be your hypotenuse, your weight, times the sine of your angle. That will give you that parallel side. That'll tell you how hard the gravity is forcing it down the ramp, in the direction of the ramp. Okay, the force that is parallel to its motion. Okay, and just like with the perpendicular component, we could also rewrite that if we don't feel like finding our weight to mass times gravity times the sine of our angle. Okay, so if you're looking for your perpendicular component, you just need cosine. If you're looking for your parallel component, you just need sine. All right, and these being physics problems, you're not always going to start off knowing your mass. You may be given a component and have to work your way backwards, but these all work like algebra. You can move them around, just like any of our other formulas. All right? Now, if we were looking for our normal force, let's think about how this block is moving. All right? If you've got this block on this ramp, it isn't going to accelerate off of the ramp, off in the direction of your normal force. It's not going to accelerate into the ramp itself. That tells us that the forces that are perpendicular to the ramp cancel out. All right? All of the acceleration of this block will be in the direction of the ramp. All right? So what that means, using Newton's first law, if we're looking at the forces that are perpendicular to the ramp, our normal component and our perpendicular component, well, they have to be equivalent. Because if they weren't, it would be accelerating one of those two directions, and it's not. Okay? So if we're looking for our normal component, well, that's actually kind of in the definition. It has to be equal to our perpendicular component of our weight. Okay? The normal force from the surface of the ramp will be equal to the perpendicular component of our weight. And this is actually true even if you're looking at a horizontal surface. All right? If it's just under the effects of gravity, all right, if we're looking at a horizontal surface, the angle would be 0 or 180. Plug in 0 or 180 there and take the cosine of it. Well, cosine of 0 or 180 is 1. So 1 times mass times gravity tells you that on a flat surface, barring any additional upward or downward forces, your perpendicular component, your normal force, will be equal to your weight. All right, as soon as you've got angles involved other than horizontal, well, then you can use this. All right, where you've got mass times gravity times the cosine of the angle that it has been inclined up at. Okay, so your Fn will be equal to your perpendicular force. So you could also use Fw cosine theta or mg cosine theta to figure out what your normal force happens to be. Not bad. We've got all of our forces on here now. Nice. But we ultimately want to know how this thing is going to be moving. All right, we can know all the individual forces we want. We want to know what its acceleration is going to be, what its final initial speed would be, using kinematics and stuff. So let's look at this next. All right, our net force. All right, definition of net force is either mass times acceleration, which is great if we know what our acceleration is, and considering that's the next one, we don't know it yet. Okay, but we do know all the other forces on this block. All right, and net force, the other definition for it, is the sum of all of your forces. Okay, so let's look at all the forces on here. All right, we're not going to include weight in this formula because we're splitting it up into two individual forces. All right, so our weight is accounted for in our perpendicular component and our parallel component. All right, so these are the two parts of our weight, and then the other force we've got acting on this block is the normal force from the surface of the ramp. Okay, and that's all the forces we have. All right, we don't need to write Fw on there because these two together are Fw. All right, now from here, because of this simplified case, because we don't have friction, well, perpendicular component pointing down into the ramp, normal component, sorry, not normal component, normal force, there we go. The normal force is pointing up perpendicular from the ramp. Well, those two are the same and in opposite directions. Okay, so if we're looking for the net force of an object on a ramp that has no friction to deal with and no additional forces, like if we had an additional applied force up or down, then we'd have to take that into account. But this is a very simplified case. All right, we've only got the effects of gravity. No friction, no applied forces. This is it. All right, so the forces total that we have on this block, your perpendicular and your normal, they're the same size and in opposite directions. So those two would just cancel out. All right, so if you're looking at a frictionless ramp with no additional applied forces, you're not pulling the block up the ramp, you're not pushing it down any more than gravity is, your parallel component, the force from your weight that is pulling in the direction of the ramp itself, will be equal to the net force on your block. Okay? In other words, we can say that your net force for a frictionless ramp with no additional applied forces would just be Fw sine theta. Or mg sine theta. Either way, it works. Last thing, figuring out how it accelerates down the ramp. Now we actually already mentioned that. The formula that involves acceleration and force would be Newton's second law, F equals ma. Okay, so moving that around to solve for acceleration, we end up getting that our net force divided by the mass of our object will be equal to our acceleration. Okay, now this actually does bring up an interesting point. Okay, because if we look at what F net gives us, where we've got that FW sine theta over M. All right, we break this down a little bit further past that. Right, that FW, that's just your weight. Weight is mass times gravity times the sine of our angle. Okay, we still got that divided by M underneath there. We got M on top. We got M on bottom. Huh. That cancels out. It's all gone. So if we want to find the acceleration of an object on a frictionless ramp, that's just going to be equal to G times the sine of our angle. The mass has nothing to do with it. It cancels out. If we used a heavier object, gravity doesn't care. Gravity continues pulling it down. The only thing that will change the acceleration there would be air resistance. But we don't really talk about air resistance because this is algebra-based physics. So if you're looking for the acceleration of a block on a frictionless ramp, easy peasy. You just need to know what planet you're on and what the angle of the ramp is. Okay? So that ought to get us through a frictionless ramp. I'm going to cut the notes off. Here we'll handle the backside on tomorrow's. All right? Whenever you're looking at a frictionless ramp, break up your weight into its two components. A component that is perpendicular into the surface and a component that is parallel down the surface. When you break them up into those components, you can add them more easily to that normal force. And because of your similar triangles, finding them actually isn't so bad. You just need to use triangle, a couple of trig functions. All right, if you're having trouble with those, make sure that you send me a message on Schoology so I can help you out. All right, next time we'll talk about this thing with friction.